So this is a story all about how my life got turned upside down. I'd like to take a minute just to hear about how I became the French Prince of Bel-Air. Okay, so this is block 2. And the first learning objective was to approximate the value of definite integrals using the Riemann sums. And I chose mostly just Hawk's questions because that was our homework. And then sometimes I would just take something from the internet or to find a correct example that I thought showed which angle I wanted to discuss. So this was to evaluate this integral by taking the limit of the associated right Riemann sum, and I wrote the right Riemann sum and what you're plugging in. So basically I worked out on giving the integral what's a, what's b, f of x, finding the delta, finding xi, plugging that in and then multiplying that out. And then after you multiply all of this out for the integral, you then turn that in and just translate that into the Riemann sum using n's and i's instead of x's as the variable, but I being the variable. So it was the limit as n approached infinity. Don't know where I got that. I used different colors, though sometimes I got a little lazy. Red is canceling out, and blue went between changes in the equation that was working through, or if there was too much blue, I just switched to green because it was basically changing the entire thing, or substitution. So it was using the sum for I squared, I cubed, just plugging those in with the values of n and multiplying that out, taking out constants for the Riemann sum to just leave I. So that gave us the limit. Once you multiplied all of that fun stuff out, it gives us the limit for 20 plus 56 over n plus 32 over n squared. And because infinity is n, and that's in the denominator, it's an, I guess I didn't write that out, but basically that is 4n to the 4th, multiplied all each terms and canceling out. So if it's 1 over infinity, that equals 0, and so that just gives us 20. For the second objective, it is to recognize, that's a little weird. Okay, I did write that out. It's to recognize the definite integrals using limits of Riemann sums. And I might have gotten these a little bit confused. And I think I did, I don't remember because I meant to switch them and I didn't. So D2 was this one, and then D1 is down here. So that above this is D2, and then this one is D1, which was to value of definite integrals using Riemann sums. And that was also using the, so taking this Riemann sum, turning that into an integral, and then switching that, pretty much evaluating that from A to B, drawing a picture, using geometry to solve that, taking that into the area because of it's a trapezoid, and that just gives us 9 over 2. So, and then this one is the definite integrals using limits of Riemann sums. It's backwards, but here it goes forwards. I don't know. It's very late. Evaluate definite integrals using the fundamental theorem of calculus. So this states basically that if we can find an antiderivative for the integrand, then we can evaluate the definite integral by evaluating the antiderivative of the endpoints of the interval and subtracting. So we have this definite integral and separating that into like terms, and then putting that term from a fraction into a just over 1 basically. And then taking the integral from 9 to 6 of each of those terms, separating that out. Doing that, you get this fun numbers, and you can multiply that out, but it's b minus a, and that's what you're supposed to do for part 2, is it equals f of b, so the antiderivative of b minus the antiderivative of a. For D4, it was to calculate the areas and volumes of geometric regions using definite integrals. So I have a lot of issues with this one, and it's just because I have trouble with finding out whether I'm supposed to use the shell method or the washer method. So this is basically the disk and washer, and it was the graph of y equals 2 to the square root of 64 minus x to the third of the x-axis about the x-axis over from 0 to 4. And so that's our a to b. And we're given our a of x, or our radius, and we just square that. So once we have the 4 and we have the regular, we can just take the 4 out, because the pi's already out, to get rid of that constant. And then we separate the terms into different integrals, integrands, and using the fundamental theorem of calculus, we b minus a, and we get this volume. So this was, for D5, it was to identify when shells or disks are needed to construct a Riemann sum for volume of revolution. And disk is best used when the curve y equals f of x is revolved around the x-axis, and for the shell, if it's y equals f of x, that's around the y-axis. Now, if it is x equals f of y, it's vice versa. So if it's x equals f of y, disk is best used if it's around the y-axis, and then shell is around the x-axis. So for this, I wrote the disk method and the shell method using a given. So I just wrote it down, and it was volume. It was the solid rotating around the x-axis bounded by the curves x equals 1, y equals 1 over x equals 1, x equals 2 in the x-axis. So we have our Riemann sum equation for disk, and we have our 1 over x of I, which is 1 over x, and our delta x is just dx. So you take pi out of there, and remember, because for disk it is the integrand of a to b of r squared, and that is what this is. So it was pretty simple to, if you know which method you're using, that takes all of the hard work out for you, and it's a lot easier to do. And it's just evaluating the integral at that point. For the shell, this was the, so I wrote down the volume equals, and I wrote the shell Riemann sum, and how that translating to if it's on the x-axis versus the y-axis, bounded from C to D, or bounded from the x-axis A to B, and how that would look. Though basically it's the same. And for the example, it was the equation y equals f of x, which equals x to the cube plus x. And it's bounded by the x equals 2 and the y-axis. So we have our a and b, 0 and 2, our height is just x, and then our length or radius is x to cubed plus x. And after that, it's just separating the terms, evaluating the integral from 0 to 2, and multiplying that out. For D6, that was to apply the definite integrals to calculate physical quantities like force, work, and pressure. And I used two different examples for this. One trying to find the work, and then one trying to find the force. Yes. So we have f of x equals x times k times x, and k is being the constant. So we have 1 over 2, and that is our feet. Yes. No. And that's the force of 1 over 2 equals 2. And basically, once you find out what f of x equals to, which is 4x, the equation for work is the integral from a to b of the force, f of x, d of x, and then evaluating that. So it is bounded between 0 to 3 because the compression was going from 2 feet, 5 feet to 2 feet. So that's 5 minus 2 is 3 feet. So you're going from 0 to 3. The second one is a 2 feet by 4 feet plate. So I'm just going to show this really quick. It was the density of water times the depth times the Ly. And it gives us the depth, which is 14 minus y. So, and we have our Ly, which is just 2. And our density is given as well. So, because 4 minus 2. And so we're going from 0 to 4 because we don't know. And evaluating that. So for D7, we are calculating the arc length and the surface area using definite integrals and rectangular coordinates. So we're given the equation and the interval which it is constant over. And if it's constant, we know what to do, and that's L equals the integral from a to b over the square root of 1 plus the derivative squared d of x. And plugging in that equation, but first we have to find dy of dx, which is just square root of x. We evaluate that. For D8, it was areas and arc lengths using circular and hyperbolic functions. We have sine and then cosine of h, sine h and cosine h, and evaluating this, finding the derivative of this, and then the integral of the cosine of h. I mostly had troubles here remembering to not erasing my negatives, making sure that I carry down my numbers and making sure they stay constant and they don't change if well, thank you.